Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. So I'd like to start off our event today by thanking Sisense for sponsoring today's event. Sisense is an integral supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Click, IBM, DataRobot, Alteryx, Tibco, and Databricks, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled Self-Service Machine Learning, to be presented by Sisense. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We have two presenters that I'll introduce in just a minute. There'll be 10 or 15 minutes of Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon, following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation, because we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speakers, Nir Regev and Evan Castle with Sisense. Now, Nir is a principal data scientist with a broad spectrum of domain expertise, technical knowledge, and a proven record in bringing ROI to companies with multiple industries, domains, and roles. He holds a Master of Science in Computational Neuroscience and an MBA and Bachelor of Science in Information System Engineering from Ben-Gurion University. Nir is also currently a PhD candidate. Now, Evan Castle has more than 15 years of experience in the business intelligence industry, spending the last 5 years in leading product-related roles at Sisense. Evan holds a Bachelor of Business Science from the University of Cape Town and an MSc in Innovation and Information Systems from the London School of Economics. So thanks for being with us today, Nir and Evan. We're looking forward to your presentation. You know, in today's demanding market, machine learning capabilities have become a basic requirement you need to support. Self-service BI solutions are no different. Users need machine learning capabilities as an integral part of the provided solution. The specific challenges of integrating ML capabilities in a self-service BI platform include the supply of ML algorithms that do not rely on specific data and can be easily applied and fit to customer-specific cases and data. So in today's Data Science Central webinar, Nir and Evan will demonstrate how to implement a classification model in a generic manner that can be used by many customers without relying on specific data and by automating the validation process, ensuring minimum overfitting. They'll outline the challenges in such a scenario and the ways to mitigate them. Specifically, the case study will demonstrate implementing a decision tree model and visualize it using a dynamic user interface component. So Evan, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Great. Thank you for that introduction, Bill. This is Evan Castle from Sisense. It's great to have so many of you joining us today. What I wanted to do was to just do a brief introduction of some of the challenges we see of moving models into production environments for BI platforms, and also introduce just a brief overview of Sisense, which Nir will be using to actually demonstrate some of the work he's done. So typically, the four primary challenges we see faced with data scientists and those of you responsible for advanced analytics in your organization is the need to actually have an operational single version of the truth, which you can use both for operational analytics as well as for advanced analytics and machine learning. The second component ties into really how to create a scalable infrastructure for data and analysis that supports both BI and machine learning, and making sure that those models that are being developed actually easily integrate with the workflow of the users in the system and how they can actually leverage them to do their jobs better. And of course, these models themselves have to be adaptable and through the system be able to be more interactive and flexible. What Sisense has provided is a solution for complex data to integrate data from multiple sources, prepare that data for analysis, whether it's for regular operational BI or for modeling purposes, as well as a capability to store that data in a high-performance engine for querying, and also the ability to actually visualize, interact, and collaborate on that data. The data itself is hosted in a single environment, and there are various components that make it accessible, whether it's ODBC, APIs, or exports to CSV or other formats. It includes the ability to also process the data very quickly, whether it's for querying, preparation, or extraction, in our in-memory in-trip analytics engine called ElastiCube. We also have the ability to actually integrate models into the workflow of dashboards where they can actually be visualized, and Neil will demonstrate part of these components, as well as making them interactive to be able to pass specific changes or parameters to get a response very quickly for the needed workflow and analysis that has to be performed. So with that brief overview, I'm going to hand over to Nir, who will get into more of the technical details.
Hi everyone, I'm Nir Regev, Chief Data Scientist and the Data Science Team Leader at Sisense. I'm very happy to be here today. I'm very happy that so many of you chose to be here today. We have a busy agenda today. We will discuss first, why do we need self-service machine learning algorithms? We will talk about the challenges of embedding an algorithm in a proprietary or BI product. We'll talk about the consideration of choosing in the black box algorithms like neural networks or a wide open box algorithms like linear or logistic regression or decision tree in our case. We'll discuss how to tune such algorithms automatically, including specifically to reduce and make sure that the system doesn't overfit. We'll see how we at Sisense integrate algorithms in Sisense UI. And also we're going to see some tips and tricks in our implementation to realize a decision tree model. Let's get going. So first of all, we have challenges. When we try to embed an algorithm inside a product, which is usually consumed by unknown customers in varying environments, use cases, domains, and verticals. One of the first challenges that the data scientist in Sisense is encountering is, yes, there's no data. This is a non-typical situation where a data scientist should cope with trying to fit and tune algorithms where there's no specific data sets in hand. Second challenge, which is also similar to the first, is the business use case. It is not known. It can vary. It can come from different environments, different use cases. And here in Sisense, we have many use cases and many clients coming and opportunities coming from different domains. Third challenge is a more technical data science challenge, and it has to do with controlling the system overfit. We'll see and dive into the details of the process called gradient descent and approximation of the gradient descent process to optimize the fit of an algorithm. Also, we'll discuss a little bit about how to interpret a model and how our users are about to interpret and understand the model behavior, the model outputs, the model mechanism. So I made a distinction between black box algorithms like neural networks, which are harder to interpret, versus more open and graphical algorithms like decision tree and linear regression, logistic regression, where all the parameters are laid open. So we're going to use an approach of automatically tune the model, the decision tree hyperparameters, specifically the mean criterion of the decision tree, which determines the depth of the tree, and we're going to use it on the fly. We're going to run a demo showing on the fly a gradient descent process to optimize this parameter. We're also going to mention the importance of performance and scalability of such algorithms, especially when they are tuned automatically and that process also consumes performance. Okay, so diving into the first challenge where there's no specific data set, it should be mentioned that our implementation, whether it's our Python, Scala, or MATLAB, it should be generic. It shouldn't be relying on assumptions or just minimize the amount of assumptions we make during coding. One of the most straightforward assumptions that we should not make is not relying on a specific column names, column distributions. And we also need to automatically make the tuning or the validation process automatic and come to an optimization of our hyperparameters. Also, one thing about features. So typically, we will handle a varying number of features in our data, and we need to think about how the algorithm will select or reduce the amount of features to the magical sort of say number that is needed to best fit the data. So I would recommend, if you're in the BI business and you're a data scientist, use algorithms that have an intrinsic feature selection, like decision tree or convolution neural network, for instance. Also, in my experience, these kind of algorithms obviously should be tested on different data sets and many different data sets coming from different domains. Moving forward, our focus today will be on the implementation, our implementation. We're going to get our hands a little bit dirty and see our implementation to this gradient descent process and building a decision tree in the most generic way that I could think of. Let's move on and talk a little bit about graphical models versus black box. So in my experience in Science, it's better to expose models that the user will understand. Usually these models are graphical, or if you could visualize the models or the processes that the models undergo, this is better. So I would pick a more open graphical models like decision tree, logistic regression, SVM, and also these kind of models are usually faster than heavier models like neural networks. So decision tree is one natural option. Decision tree can be explained graphically. And just to drill down and talk about a little bit about the decision tree, we'll take, for instance, this decision tree, which is being ran on a data set called Arif, which contains flowers. So a decision tree algorithm basically will search recursively the most effective partitions to maximize some criteria, whether it's information gain or Gini index. So, for example, in this data set, we had 65 setoses flowers versus 75 flowers which are not setoses. And from the first partition, partitioning on the petal length, you can see that the system were able to separate the setoses into a group of 55 in the left subtree and to a group of 10 on the right subtree, which is pretty neat partition. Usually the best partitions are on top of the tree, and as the tree goes down, the partitions information gain becomes lower and lower. So this is a more visual way to just present the separation of the first partition in the tree between the setoses and the other flowers. We'll just move on and to summarize the pros and cons of decision tree. So they're graphical, which is good to the users. It's more digestible, more understandable, and the users can relate and can interpret the path of the tree into business context, business rules. They can actually pick a subset of the tree path and adopt them, maybe transform them into a business rule. And so these models are modular, which is a great advantage. On the other hand, decision tree tend to overfit. So we will see how to handle that. So that's actually an opportunity, was an opportunity for my team to see how we overcome the overfitting on different data sets. And also, one other advantage is the feature selection. In a decision tree, this is an intrinsic mechanism relying on the index, the information gain, or the Gini index, and being able on the fly to prune or not to create, while building the tree, not to create partitions which are less significant or have a lower information gain. So this is good for on-the-fly machine learning algorithms because we don't have to worry about feature selection. But if you do want to pick another algorithm and to do feature selection, you can use standard methods like correlation metrics and scan predictors or explaining variables that have high correlation and remove some of them, or you can run models like regression plus regularization to see which variables are most predictive toward target variable, and which have a coefficient which is close to 0 and exclude them, and so on and so forth. But in our case, the pruning of the tree, which is an intrinsic part of building a decision tree, is a great feature, and we'll use it and show it in the demo. So let's talk about the main theme, the main principle of today's session, demonstrating how to automatically tune an algorithm. So taking a decision tree, for instance, it is very easy to go forward into the right part of this plot, and as we add more and more variables and more partitions, we're prone to overfit. The magic is to identify the spot where the error curve, which is the red curve, is approaching to a minimum. So this is something that I will try to demonstrate with my implementation. But usually the meaning of overfitting is when we add complexity to the model, when we add parameters and variables, our accuracy on the blue curve, on the training examples, becomes higher and higher, or the error is coming down, which is good. But at some point, from the middle point on, the training accuracy keeps going up, but the test sample accuracy is starting to go down, or the error on the test sample is starting to go up, and this is where we are starting the overfitting. So just to recap, I think the purpose is to implement some kind of a gradient descent process to be able to slide down the error function with the opposite direction of the gradient of this function, of this curve. Okay, let's talk about the data. So we have a very nice and clean data set called the ARBIS data set, which contains 271 observations about flowers, about irises. And it has three classes. It has the setosa class and other two classes, which I've grouped into one class. So the purpose is to classify whether a flower is a setosa flower or not, using the petal length and these other features. And also I've added another three features that just to add some confusion to this demo. And I'm asking you to think about why have I added three random variables. These variables are variables that I've simulated, that I've created from some uniform distribution to demonstrate some principle that I've discussed earlier. So I encourage you to think about it. So this is the problem. So this is the iris problem, iris data set. The purpose of the problem is to classify whether a flower belongs to this species called setosa or not, or belongs to the other two species. This is going to be the demo today, and this is our implementation that is pre-processing the data. Let's drill into it and see that, first of all, we need to parse data from an external source. So the most generic way to receive data, I think it's a list in R. So I'm assuming that the data is coming in an object, in a parameter called arg, which is practically a list of lists. It's a list where each element in the list contains a data column. So here you can see in the red circle a neat one-liner way to parse a list into a data frame with the help of the mapply function and the vector C, the vector function, turning the list in a one-liner into data frame. And this does not assume anything about the list, the length of the list. It could be a 10-column data set, it could be a 100-columns data set. So I think this is pretty neat. And also, if you go down a few lines to the lower black rectangle containing code, you'll see that I've constructed a formula with the as formula constructor, and I've not assumed anything about the names of the data. The only assumption I've made here is that the target column, the species of the flower, is last in my data set. So this is the reason why I'm constructing the formula, where the first part of the formula will be the name, whatever name it would be, of the last column in the data set. And then I'm concatenating a tilde and a dot. The dot notation in R means take all the columns in the data and try to fit them to predict or classify the target variable. This is a neat trick that I've learned recently, and you can try to use it on your own data and use cases. It should work. Let's move on to the heart of the system, which is basically a gradient descent process that is trying to optimize the tree depth with controlling the mean criterion parameter, which is actually a parameter which equals to the 1 minus the p-value of the statistical test to determine whether this prediction is due to be performed or not, according to the criteria, the information gain, or Gini index, or other criteria. But basically, as we take down and reduce the mean criteria, we're actually increasing the p-value, so our null hypothesis could be rejected more easily, and more partitions can be created. So you can see in the right lower corner, you can see the overfitting, underfitting curve. So this is the direction of the process from left to right, where we add more and more partitions as the mean criteria is going down. Each iteration, we're enabling the decision tree to use more and more partitions. So let's drill into the code, and we can see that we have a loop, a while loop, that contains two basic conditions. The first condition is not mandatory. I added it just to make sure that we have a compliance of the training accuracy versus to the test accuracy. We usually have a compliance of 5%. It means that the training accuracy should be larger than the test accuracy by 5% or more. But you can change that according to the compliance of your company. But actually, the more interesting condition is the second condition, which is testing whether the previous iteration test error is larger than the current iteration test error. Or in other words, is the previous iteration accuracy is smaller than the current iteration accuracy. If it is, we should keep sliding down the curve of the error or the accuracy. So how do we do that? If you can go to the last line, you'll see that I'm taking the mean criteria in each iteration. I'm taking it down by 0.01, which is just an arbitrary learning rate that I've chosen, but you can also try to optimize this parameter. Just to simplify things, I've chosen 0.01, which is a pretty standard learning rate. And basically, this is the heart of the gradient descent process. We'll shortly demo how this is working on the fly, and we'll see how a different tree is being created each time I run this. And also, there's a question of why this is happening, why different decision trees is being built with the optimized mean criteria, but we'll discuss this later. But this is actually what is happening under the hood. Also, importantly, there's the decision tree building. Let's go over it quickly. So first of all, and this is a tip or a hint for you, for each iteration, we are partitioning the data into a training and a testing set. When we'll do it randomly with the create data partition function from the caret package. And after we're doing this, we are passing to the C tree function, which is in charge of building the tree. We're passing it the mean criteria arguments. Okay, the mean criteria that is currently being selected in the current iteration. And then, in a generic way, just notice that I'm not using any specific details about the data. I'm building the decision tree using the generic formula that I've created in the previous slide. I'm passing the data, which is obviously the training set, and I'm passing the control parameter, which contains the mean criteria. So the decision tree in that point of time is being constructed. And then in the next slide, I'm starting to peel off and extract some statistics and performance KPIs. First of all, I'm predicting the species, the target variable, using the decision tree that I've just built, and running it once on the testing data and secondly on the training data. So I have two kinds of predictions, and I'm constructing a confusion matrix built on these two set of predictions. Just to recap, I have a predictions set based on the training. I'm trying to predict the label of the flower on the training set, and I'm trying to predict the label of the flower on the testing set. Then I'm extracting the standard KPIs, like in this case, the accuracy from the confusion matrix. We have two confusion matrices. We have the test confusion matrix, cm.test, and we have the training confusion matrix, the cm.train. And basically, I'm calculating common KPIs like specificity, sensitivity, and most importantly, the train accuracy and test accuracy. So basically, this is what's happening under the hood, and we'll shortly move on to the demo and see how this is running on the fly. But first of all, let's discuss about visualizing this entire thing on Sisense UI components. Here we needed some post-processing. Let's move on and see what kind of post-processing did we use. So after searching thoroughly through the web, I've taken into advantage the D3R package, which can actually take a decision tree package, decision tree object, and parse the structure of the tree into a JSON object, which is easily utilized in our web component, web UI. So this is what is happening in the first line. I'm calling the function D3 party from the D3R package, and I'm passing the CT, which is just a decision tree object. This is after all the optimization had taken place, and we have the optimal depth, the optimal tree, and now I'm post-processing to build a UI page displaying this tree in a neat, dynamic manner. So I'm passing the C tree. Now I have actually
Yeah, we seem to have lost your audio.
Yeah, I'm sorry for a little difficulty, but a little technical difficulty. Now I'm back. Sorry for that. So let's move on. So after passing the C tree into D3 party, we have the tree we have in a JSON, and we're writing the JSON into a file. Then we're just calculating the predictions on the result set to return to Sisense if the user chose to actually preview the predictions and not the visualization of the tree. And basically that's it. We also have a plot tree little function that I've written here to plot the tree and plot some statistics about the selected optimized mean criterion that were actually selected by the process that I previously demonstrated. So I think in that stage we have another 10 minutes to go, so we'll go straight to the demo. And I will share my screen, and in a few seconds, I hope, not minutes, you'll be able to see my screen. And we will see the Sisense UI holding the decision tree, and it will come. It is now coming, and okay, so this is what the decision tree that I've just ran. I just refreshed the browser and built a decision tree after running the entire gradient descent process. So this is a decision tree containing probably the optimized mean criteria. And this is a very neat way to traverse and display a tree. You can see the root node from the left, and you can see the first partition on the petal length, whether the petal length is greater than 2.04 or not. So let's take the path of the petal length is smaller than 2.04. We can see some interesting statistics like how many data points are in that subtree. So there's 57 data points. We can see the p-value of that partition, of that statistical test being done to establish whether this partition should be made or not. We can go further down the tree and see that now we are partitioning on the petal width whether it's smaller than 2.52 or not. So we'll take the path of the petal length is lower than 2.52. So here we are approaching a leaf node containing 7 observations. We have a probability of 71.4 that this 7 observations, this set of 7 flowers will actually be setosa. So the system is 71.4 confident that these are setosas. And actually, you can multiply 7 by 0.71 to get an approximation of how many setosas are actually here. If the tree is quite deep, you can traverse on it and close nodes and open nodes that are, or subtrees that are specifically of interest in the user. And this is a very cool way, both for a data scientist or a data analyst, to traverse and learn the outputs of the algorithms, and both for productization when we are trying to sit down with our users and communicate the results of the models, try to productize our work, and turn this entire thing into an actionable set of insights. I can tell you from my personal experience that some of the users that I've been working with chose to adopt and choose specific paths that were more interesting and had a more actionable prospect and turned them into a business rule. Okay, what's more interesting, that some principle that I wanted to share with you is what happens if I hit refresh to the browser. So you can maybe or maybe not see that a different type of tree is actually a deeper tree was created this time. This is an interesting phenomena that has a very, very straightforward explanation, but I'll leave it to you to figure it out, and you can ask about it if you're interested, and I'll be able to explain what is happening. But actually, each time I will press the refresh button, a different tree with a per se optimized tree with an optimized mean criterion is being selected. Maybe we'll do it once again just to, for those of you who are still having doubts about this. So this is happening on the fly here. Well, this actually looks a little bit similar to the last one. Maybe I'll do it again. Okay, this is a different tree. This is a less deep tree, and I hope I could convince you with this interesting phenomena. And again, it has a very straightforward explanation concerning with the data that I'm using for training. Okay, let me also move to my file system just to show you that each time I ran the tree, a different decision tree. Each time I refreshed the browser, a different tree was created with a different criteria. But you can see that that most criteria are around 0.17, 0.18. This is the neighborhood of the mean criteria, and this is strengthening my belief about how this process is functioning. So returning back to the deck and resuming my demo. So I think, Bill, that in that stage we can turn to the Q&A session. We have about 15 minutes. So I will wait for Bill to announce. Yeah.
All right. Well, Nir, Evan, thank you for that excellent presentation. And I'm going to move us to this slide, which I'll leave up during the Q&A session so that you can contact Nir and Evan if you choose to after this presentation. I want to thank the audience for their participation. We've had a lot of questions that have come in. and we'll do our best to get through all of them in the time remaining. So let's get started. Nir, you threw out one that we have to ask about, and that is why each time you refresh the R, you got a different tree with a different min criteria value. Can you tell us what was going on there?
What is going on that in each iteration, maybe I'll go back to the slide where I have the code. In each iteration, trying to optimize the min criteria, I'm actually partitioning the data randomly, stressing on randomly into training and testing. So actually, the training data set is keep changing from one iteration to another, causing actually for a different tree to be created each time. So obviously, the entire process of optimizing the min criteria is a different process because different trees are being created. So obviously, the result of the optimized min criteria and the optimized tree depth are being different from one browser instance to another browser instance. I hope that answers the question.
Yeah, thanks for that clarification. Let me move us back here so folks can see your contact information. Now, the audience has asked a question about speed, but before we get to speed, I may have missed the part where you talked about whether or not Sisense is typically on-prem or cloud. And then I want to ask you a question about how long it takes to respond to certain data types.
So Sisense are both on-premise and on-cloud. And about the performance and scalability of this process, it's been done on a rather small data set of tens of thousands of records. And it's usually could take between 30 to 60 seconds on this kind of data set. We can adjust some of the parameters to optimize the speed, but basically determining on the learning rates. Also, if the learning rate is very, very small, it means that we're going to have many, many iterations, and the entire process will take longer, but we earn the chance to not hitting into minimum, a local minimum, while searching on the error function, error curve. So that's the pros and cons of selecting a smaller or a larger learning rate.
Okay, well, thank you for that answer. Now, you have used R in your example. Can I integrate other scripting languages like, well, Python is an obvious choice?
Well, currently, we invested most of our integration energies into R, but we're approaching for this end of the year a project of integrating Python into the product. So this is currently strong on our plan, on our roadmap. However, currently R is supported.
Okay, understand. Now, earlier in your presentation, you talked about the ability of Sisense to build models that, for example, don't yet have variable names or don't have a specific business use case, that they are generic in some way. Can you explain how that works?
So basically, Sisense have thousands of customers and opportunities that comes from different domains. Each of them have different data sets with very different characteristics regarding the distributions of the data, the types of the columns. So giving thought to this type of job, we needed to come up with the most generic implementation of the algorithm And we need to come up with algorithms that both can be consumed easily, and under the hood, they could be tuned rather fast and automatically. So this is the reason why we chose a rather fast implementation for a decision tree and a relatively fast optimization, gradient descent approximation process.
Okay, good. I understand where you're what you're trying to drive at there. Now, does your user then have to write new R code for each application?
But we have two approaches. The first approach is totally self-service machine learning giveaway algorithms like that one. However, this first approach is extendable, and a user can certainly go into the code. The code is open, and he can both develop code on the front end, integrating R and Sisense on various Sisense widgets, and you could also embed R code on the back end, interacting with Sisense database called ElastiCube. So we have a number of approaches, but actually the first one, the 100% self-service, is the hottest, maybe if you can put it this way, the hottest approach, just because it's fast, it has an automatic tuning processes, and it's really fun to use and to productize.
Okay, thank you for that clarification. Now, we've focused a lot on decision trees, but earlier in your presentation, you talked about other types of interpretable models. Obviously, GLM comes to mind. Is GLM currently available in Sisense?
Actually, every algorithm or code maybe that is available through the R CRAN or maybe external to CRAN R packages could be used in Sisense. There's no limitation about over the code that you choose to embed. So GLM is certainly one natural choice to either use as a prediction or a classification model. It can also, in that case, we had a case where we had two classes, but there are also cases where you have more than two classes. So you could use GLM both for regression or classification for a situation where we have more than two classes. But basically, you can also embed a neural network in NNet and SVM, CARE package. All the CRAN packages are wide open, and this is totally integrated to the open source platform.
Okay, I understand. Well, thank you for that answer. Now, you also talked about automating the data mining validation process. Could you talk about how you go about automating that? Okay,
so part of the validation process is controlling the overfit. Okay, so when I do validations, usually, and it doesn't matter which model I'm using. I'm currently working on deep learning, so I'm constantly monitoring my training loss versus the validation loss, and from the behavior of the development of these losses, I can spot and validate how my model is trained and whether it's overtrained, overfit, or underfit. So when I say validation, I mean the optimization of the parameters that determine whether my model is being overfit or underfit or perfectly fit.
Okay. Oh, I understand then. Thank you. This whole market issue of self-service machine learning, can you comment on why this is becoming such a hot topic in platform development these days?
Yes. So there's a little bit of an echo. So basically, Sometimes machine learning, I think it's deriving from a few trends. Data is keep growing and growing. There's massive amounts, I think around 250 exabytes, which is 250 million gigabytes produced every day in the world. It's coming up every year, more and more. There's more and more awareness to data-driven products in the industry, and we see that trend at our clients' requesting more and more self-service machine learning self-service products. And there's also developing trend within the analyst domain, trying to understanding that many of the problems that couldn't be solved 20 or 15 years ago can be solved today with machine learning, specifically with advanced technologies like deep learning. So all of that said, plus the fact that the number of data scientists is not coming up at the same slope or trend, is causing more demand than supply to services and products in the machine learning industry than what could the data scientists could fulfill. So I think the trend in the data scientist domain will shift from developing and practicing specific problems with specific algorithms to a domain where data scientists will develop a meta algorithms that can fit itself and tune automatically some of the hyperparameters and being able to match that algorithm to different problems with different data sets and domains.
Yeah, you're hitting it at an area that I'm very interested in. It's kind of the split between automated machine learning and deep learning. By the way, the audience asks, since you said that Sisense would support all the R functions, does that include the deep learning functions in R, perhaps even CNNs?
Well, to be perfectly honest, I'm not using deep learning with R. I'm using Python with Keras over TensorFlow, and I'm not very familiar with neural networks, deep learning neural networks in R. I know that there's the NNet package, but again, basically whatever is available in R and CRAN or external to CRAN could be used in Sisense.
Right, right.
Although
so,
I wouldn't recommend using neural networks in such scenario in a proprietary product or a BI product, because these kind of models can take long time to train, days or even weeks, depending on the learning rate and batch size and other hyperparameters, and of course the data size. So that's not a typical most convenient usage of neural networks in that scenario.
Right, that would work against your philosophy of creating interpretable models, and of course R probably is not the best platform for doing deep learning. We'd obviously default to Python or something like that.
You can say that again.
Yeah. A question from the audience. You showed the splitting of your data into training and test, and this audience member is asking. He's getting new data every day, which implies that there might be some change in his model. How do you keep incorporating new incoming data into a model to make sure that it is continuously updated?
Oh, that's an interesting question. Interesting question in the context of decision tree, because usually decision tree have to be run and built from scratch. I don't know any way to iteratively use the last state of a decision tree and feed it on new data. Maybe that is possible, but it's not the first thing that comes into my mind. But if it's another algorithm that have a specific set of variables and coefficients, that specific person can develop a process where you can spot or monitor the change of the coefficients from the last model instance and compare it to a new model that is being created on the fly on the day that the new data is coming, and to determine with a simple statistical test whether these set of coefficients have changed significantly, and if so, rerun the model and take the new model instance and update it on its production environment.
Right, right. And it was not clear that that audience member was asking about real-time or streaming, but let me ask that question.
Mm-hmm.
Is there a way that Sisense can handle streaming data, for instance, being integrated with Spark in some way?
Yeah, that's an interesting question. We are approaching, we have concrete plans on our roadmap to approach this direction, and we also already support open streaming connections that are directly connected to external platforms that can stream data in real-time mode to our cube, Elastic Cube, which is our database. So this is something we are currently supporting, and we're also approaching aggressively the direction of supporting parallel computing platforms like Spark to maximize performance, of course.
Well, those will certainly be interesting developments and would address the question that audience member asked. Are there trial versions of Sisense that are available?
Trial version? Can you rephrase that?
Yeah, trial. A test. Is there a way for
trial.
An audience member to? Yeah, trial. Yeah.
Of course. There's a bunch of them. And there's also a 30 days, right, Evan? A 30-day trial, for free, of course, with a significant amount of support and guidance. So any of you that wants to be an opportunity, you can make it happen. You can download it real fast and easy and get support and guidance through the process of setting up an Elastic Cube and setting up a dashboard. These kind of processes can take a little amount of time. This is one of the Sisense pros and significant advantages in using our product.
Well, Nir, Evan, hey, thank you. Those were some great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll send those unanswered questions to Nir and Evan and the Sisense team so they can follow up with you after today's webinar. I have just a few quick announcements. If you would please mark your calendar for July 25th. That's our next DSC webinar, which will be a language for visual analytics, and that's going to be presented by Tableau. Also, remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab, which is located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to Sisense for their sponsorship and our speakers today, Nir Regev and Evan Castle, for their insight into today's topic. So my name is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on July 25th. Have a great day.